Okay, so welcome back for the second talk of the afternoon session. So next speaker is Suman and he'll tell us about brick wall, normal modes and emerging further.
Thanks for this opportunity. This is the title of the talk, Work Done in Collaboration with Various People. And I know that many of you heard this talk from our organization maybe, but I don't have anything new to present, that's why I'm presenting it. I'd like to start by showing these two images, and these two images are very familiar to you. First one is by LIGO, and the second one is by Universal Telescope, where you can see the infinite of black holes, the existence of black hole, and in this picture you see the horizon also. But considering the observational precision, one might ask, could this be the result of a black hole, or perhaps it's coming from an extremely compact object? Or maybe to what extent can an extremely compact object mimic the properties of a black hole? There are other motives, like black holes are chaotic objects, but to show this for E greater than 2 is very difficult to show, because in E equal to 2, the ZT is dual to SYK model, and we can compute the spectrum of the SYK model and can make spectral analysis, and to show that the spectrum of SYK model is chaotic by showing that the spatial distribution is Wigner-Dyson, or maybe by showing that the spectral compactor contains a linear RAM of slope 1 in the log log log. But to see this from the higher dimensional black hole, let's say 5-dimensional black hole, what we have to do, we have to solve this n equal to 4 theory, which is hard. And to see this from bulk side, we have to solve quantum gravity, which is harder.
So I didn't understand this question. You could just compute the bulk out of time molecule, right? You don't use the spectrum usually.
Yes, I see. So, simpler question is there any evidence in the probe sector? So you can compute the OQC. But OQC is a measure of early time scales. So my question is like how to see that this is chaotic at late time also. And maybe one of the measure of this late time chaos is spectral compactor, and the linear ramp in the spectral compactor indicate that the system is chaotic. But if you now, and for this, you need the spectrum. Now if you quantize the probe scalar field in the black hole geometry, this will give rise to quasi-normal fields. And these are complex valued number. So if you compute the spectral compactor, you will get a decaying spectral compactor at the left time. We do not have any ramp and so what alternative approach can be done. So what we did, we quantize the probe scalar field in the black hole geometry, but with the brick wall boundary condition instead of the more familiar ingoing boundary condition. And the interesting fact is that then if you compute the mode, these modes are a real number, and if you compute the corresponding one single particle spectral compactor, this spectral compactor shows a linear ramp. So it's not the solution of the main problem, but it's interesting. So let's focus on this aspect.
So is it genuinely linear, or is it linear on average?
So these modes are numerical number. So you can plot the spectral compactor, and so this you have to do numerics. You do not have any analytic way to show that.
That's true.
It's exactly close to 1.
So I think I thought my understanding was that for a chaotic spectrum, the linear ramp only emerges in like some Gaussian sense, and I think that there are very big fluctuations around the linear.
Yes, fluctuations.
And you get
I'll show you the
also?
picture.
Okay.
So, as our main measuring spectral compactor, let's define the spectral compactor. So it's defined by this equation 1, where Z beta T is the partition function, where beta is analytically continuing to beta plus IT, where beta is the inverse temperature, T time is the Hamiltonian of the system. So if you know the spectrum, you can in principle compute partition function and its G. There are some generic properties of spectral compactor, like if you have smooth density of state, this leads to Hamiltonian spectral compactor at late time, and if you have discrete spectra, then you will get a non-Hamiltonian spectral compactor at late time, which is called Levy. And if you have Poisson distribution of energy level, this generally gives rise to no ramp, but if you have a Wigner-Dyson distribution, this will give rise to ramp of slope 1 in the log. So our model and picture of our model. So
So can you little slide? So smooth density of states leads to vanishing.
if you post can like if you write density of state instead of
What is a
actual
smooth
number.
density of state? What is smooth density of state? What does it mean?
If you post grain, so if you do not see your the gap between the spectrum,
And if the spectrum, gap spectrum is
I mean, it's continuous. This
Yes.
continuous density, you have continuous density. Like
we
really
don't have any gap.
oh, okay, if you don't have any gap.
Continuous, yeah. If you,
Oh, okay.
so we have ETC black hole background. ETC is because it's simpler to do the calculation in three-dimensional black. Then we put a brick wall at some position, let's say at R0. So our geometry is not the full geometry. Our geometry is from R0 to infinity. And so this model do not have any horizon. And we quantize the probe scalar fit in this region, in outside so it's from R0 to infinity. So mathematically we have this metric. And we are quantizing a probe scalar in this geometry, so we are basically solving this box phi equal to mu square phi this equation, where mu is the mass of the scalar thing, and we are imposing these two boundary conditions. First one is the normalizable boundary condition at the boundary, which is standard, and second one is at r equal to r0, where the peak wall is located, impose the boundary condition, the field is zero. And so there is some infinite potential level, and that's why the field is zero. And the existence of the peak wall in the problem enters through this boundary condition. And this gives rise to normal modes as opposed to quasi-normal modes, because in general, in black hole geometry, if we put ingoing condition, that means that there is some loss in the system. And as there is no loss in the system, this is like a scalar fit in a box. So you will get real valued numbers if you quantize the scalar fit. And these real valued numbers are called normal modes, and these normal modes are labeled by two quantum numbers. One is n into the periodicity of psi coordinate, and another is n, which is the principal quantum number. Now this is the spectrum along n and m direction. So along n direction, the spectrum is linear, and as a result, if you plot spectral form factor, you will get the similar spectral form factor as you get for simple harmonic oscillators. And the level distribution is also same as similar.
So you are interested in seeing how well the equal boundary conditions mimic the
Mimic
black
black.
hole.
Yes.
So if you find more normal modes, quasi-normal modes, doesn't that mean there's a big difference?
Yes, yes. So now, if you have quasi-normal modes, then you will get no ramp and breaking in the spectrum.
Quasi-normal modes are some more normal modes. I mean, you can always quantize in the black hole also to get normal modes by putting no boundary condition at the horizon. And then the quasi-normal mode you think of as some linear combination of these waves. I mean, you look at the pole in the wave function in the complex linear, and those positions of those poles give you the quasi-normal mode. So you
They need to be off of the real axis.
they are off of the axis. So maybe the idea here is this is some discrete approximation to that spectrum. That you would have got a continuous spectrum if you didn't have a big word. And some of this discrete approximation to that continuous spectrum.
You must just ask what is the imaginary part of the whole, right?
You will have to compute the full wave function, and you can ask in the wave function. You will get a term which will look like e to the I omega t and e to the minus I omega. I guess near the brick wall, there will be something that could have gone like e to the I omega r star. And
Yes,
e to the
one is
minus I
ingoing,
omega star.
another is outgoing.
And the ratio of those two will have a pole in the omega axis, and that is usually the position of the quasi-normal. If you look at the ratio of this wave function and that wave function.
The ingoing and outgoing.
Yeah, and that has a pole in the omega plane. And that is the position of the quasi-normal. If you have
In general, when we compute the quasi-normal mode, we impose the boundary condition that you do not have any.
yes, but there's another way to quantize.
Let's say you have T and T. T is zero.
No, there's another way to quantize, which is you put no boundary condition at the horizon, which is actually how you get Hawking radiation. So you put no boundary condition. Then you will get both an ingoing mode and an outgoing mode. The outgoing mode is actually the Hawking radiation. And the ratio of those two we'll have a pole in the complex omega plane, and that pole corresponds to the quasi-normal mode frequencies. So you might also see it.
Is this equivalent to this poles of the normalizable mode over non-normalizable mode? Because this
No. There's you always normalizable boundary conditions at infinity. This is at the horizon.
You have two modes, P and Q, ingoing and outgoing.
At the horizon.
At the horizon, the ratio.
But once you have imposed reached the boundary condition, then it may be hard to recover the quasi-normal mode, right?
In this case,
In this case, yeah.
This
Because there is a recoil, right?
yeah.
Maybe you have to somehow take the limit of the recoil going towards the horizon.
Yeah. I don't know if you can recover in this case.
Right, so in this paper by one of the things it does is it relates two-point function to the spectral form factor, and as I understand it, the polynomial mode decay of the two-point function is like the slope in the spectral form factor, right?
What's normal increase of the two-point function? Is the previous slope.
Yes, it's the slope, the part before the ramp. And so I'm just wondering how you, suppose you did a story 2D, where this analysis applies, then who would you get a slope without getting polynomial modes, where at least as there is safety?
Normal mode to get the slope.
Huh?
Because if you have some real, if you have some spectrum, some quantum mechanical system on dimensional, and if you have the spectrum, you will always get the slope part.
No, the slope part is highly non-universal, right? It can be exponential or polynomial.
Oh, this is how the slope.
Yeah, the polynomial mode decay is the fact that you get exponential slope. Maybe it's wrong, I haven't studied that paper before.
I think the slope is just decoherence, right? I don't think that's so accurate.
Huh?
The slope is just decoherence, right? It's the fact you start with some wave packet that's coherent, and then you let it evolve, it will decoherent.
Yeah,
So
that
it
is
will
true,
go
but the question is about the decay. Is it polynomial exponential?
It might be very universal.
It's very non-universal.
I don't think
The rampant plateau are much more universal.
I don't believe that.
Huh? Like people have studied other chaotic systems and they find other behaviors. There are systems without a ramp also because the slope takes
The ramp is actually not perturbative, but the slope is just at early times. It's early time decoherence
Yes.
with s degrees of freedom.
Yes.
It would be very surprising you're saying it. That is,
No,
you have ETS degrees of freedom and they decohere very fast.
no, but people have like studied different systems and get like different forms. Because the early time stuff is about very far away energy differences. Whereas the plateau is about very close by energy differences. So magnetization is about close by energy differences, not about very far.
I mean, I would think it would correspond to some general thing like a specific heat or something. Like, you do some random phase approximation, you ask for some derivatives or something like that. Like some gross features of the energy spectrum.
That sounds sensible, but I'm just saying that you get different problems.
Yeah, you can, in granometics, say you can just consider different potentials and change the early slope to different powers.
Yeah, different powers.
Yeah.
But so you fix some parameters and you will get the slope correct. No? Some one or two parameters you have to figure.
Yeah, so for example, in Hermitian, like this quadratic granometics theory, you will get t cube, 1 over t cube. But then you can shift it to t to the power 5 or t to the power 7 by adding appropriate potentials and tuning these parameters. So it depends on edges of the 1-point density function.
Does it mean that if you do not have quasi-normal mode, then you cannot get
And yeah, maybe we can just look at Silsa's paper because I am not super familiar with it, but I know this is one of the points that I think.
Yeah, I'm a little more concerned that you get this ramp and plateau because that is a non-perturbative effect which might be pretty non-universal. Like there's no universal argument at all that you will get this ramp.
Magnetization is difference.
Does that give you a ramp?
Oh, I'm sorry, because of that.
The plateau is kind of obvious, so e to the minus s by 2, that's also random, this random phase. The fact that you get e to the minus s by 2, that's random phase. That you don't keep. So all this ramp.
Especially with our field theory, right? I mean, but his calculation was
It's quantum mechanical because it's like particle in a box. You are solving box pi equal to 0. So it's basically a radial equation and you are inputting two boxes.
semi-particle
So when does the linear ramp kick in here? Like how much does the spectrum decay before it kicks in?
I mean, it's time scales.
No, yeah, in magnets you start with order 1. And bend as the ramp vector. The slope that you have, how
Oh, I mean, what is the ratio between this number and that?
Yeah. So that's an important number because that should be some number that's larger than the entropy of the black hole. And I don't think you'll ever see that in your approximation. So in the boundary, it should fall. And the plateau is at e to the minus s by now. But you won't see s in this whole calculation.
No, I mean, S is like relation related to the gravitational constant.
Yes, it's the entropy.
No, I mean, we don't know how it scales and how it led to this G Newton or.
Aren't you fine tuning the cutoff to some Planck scale thing so that S comes in the spectrum?
To get the proper entropy, proper area of entropy, you will have to fix.
And that's the same number that should appear here somewhere. That cutoff an angular momentum that you put, it will have to be the same thing.
So just I don't know the thing. So non-trivial deep plan, like which one? The middle dark, each one is a non-trivial deep plan, right? This is the
So this is the slope part, then this is the ramp part, and this is the
ramp, but this is what you are calling ramp post non-trivial, okay? And this is the numerical result.
But you can feed the spectrum very well with the log spectra, and for log spectra you can actually very accurately numerically found that the ramp is slope on ramp, because for log spectrum the partition function is like the zeta function. So this is becomes zeta beta plus it zeta beta minus it by zeta x zeta beta square. So from there you can compute the slope very accurately, and it's very close.
And do you have a plot of the spacing distribution?
Yes, this is the level distribution.
Level spacing distribution.
So it's like Wittgenstein you can say, because at s equal to 0 it's 0 and at s equal to infinity it's infinity.
So whatever you are calling this deep ramp Plato structure, this is just the Fourier transformation of the spacing distribution, right? Or not? It should be, right?
2-point function.
No, it is not 2-point. This is already 2-point spacing.
No, I'm saying,
I'm saying that this spacing is already the difference. So this density function, this is the Fourier transform of that density function is GP, isn't it?
GP is Fourier transform of the density function.
No, density, no, one. It is
So other two partition functions. Mod z, mod of z beta to z t squared. Those two partition functions.
So you look at this here, you can say.
no, the point is that if density of the difference, how many times difference comes?
But that's what he's saying, right? This is not exactly what it is. There is a relationship between the level spacing and etc. But actually it is not really a Fourier transform factor, but also differently because the density. Which also has the same implication in it, I think.
No.
Right, because it like shows about correlations about
Yeah. So that's not clear.
not clear, it's like.
So one interesting factor is that along any direction, the rate of growth of omega is very small as compared to along any direction. So there is some quasi-degeneration behavior along any direction. So yeah, this is the level spacing distribution plot. This is not the well-known Wittgenstein for zero and zero, but you can say the Wittgenstein extreme Wittgenstein because at s equal to 0, zero and s equal to 0 is also known. And we know that averaging decreases with fluctuation. So if you take the random average here also, and here the only parameter you have is the epsilon, which is the position of the brick wall. If you random average over this epsilon over Rx, and then you will get this vector form factor. And this is some discontinuous thing here. This is because the position of brick wall is not very close to the horizon. If it's very close to the horizon, then these things vanish and it becomes smooth. And this is the slope on line.
Sorry, you're saying position of brick wall is not close to the horizon.
Yes, and so here in this picture, what is the value of zeta?
Like
No, let's say z0, z not equal to 0 is the position of the horizon. Then, and this is for, let's say 0 equal to, let's say 5 or 6. If you decrease this, then these things also decrease.
So you don't need to set Z0 to a Planck scale, Planck.
So for this no, I mean for this numerical thing, I mean, so the thing that will happen is that if you move your Z naught towards the horizon, you will see that your slope changes and is set very close to 1. Now if you change Z naught, then this slope doesn't change that much.
So what is the scale of Z0 you're using in terms of Planck scale? G equal to 0, D equal to 1?
Because Z naught here, like in our scale, Z naught is 10.
So retain what is what you
You can say R, if R naught is the position of the equal and R is the position of the horizon, then like it's 1 equal to the when your equal is on the horizon. So any number, let's say 5, 6 or 10 like that.
Sorry, this should be on the invariant, right? There's an invariant distance between the horizon and the equal. What is that?
See, no, I mean to match the entropy, you have to fix this proper length between the position of the horizon and position of the equal to be Planck.
Yeah,
But
okay.
here it
So you're saying you're using
because not numeric is stable enough, so that you can change your Z now. But this RAM, the slope of the RAM is not changed once it gets very close to 1.
So you're saying that you're using different breakers for different
Yes,
directions.
different position of the equal, and I am changing the equal position, and I am computing the normal mode, and see how is there any ramp or no ramp.
So you're getting the plateau also, right? But the value of the plateau should depend on the entropy.
Yeah.
Yes, we are now trying to try
Cannot
that,
be
but
independently.
yes, but here how to define the
I mean, the physics, it should be dependent on the entropy. So somehow it should be that when you fix the distance of the brick wall,
so
it
it
changes the value.
depend on Z cut and kata. Yeah, but we tried this thing, but there are some numerical because there are some noises. That's why we were trying also because, and we are also trying to find how this deep time scales with epsilon.
Sorry, but so you're saying you're doing the spectral form factor calculation in a regime where the level spacing is not equal to minus.
Level spacing is now e to the minus.
Because to get equal to minus as level spacings, I thought you would need to send the record to Planck level.
Definitely not e to the minus. Even then you would not get it. You would get 1 over s.
So you get polynomial mass.
Yeah.
Oh, okay. Then how are they getting the entropy right?
The entropy you get because there's a lot of degeneracy.
Yes.
Oh,
and then
I see.
You kindly cross it because the talk is completely ununderstandable. So let me cross it because anything is not clear. So please go ahead.
In the regime, when your R is over A is order 1 number, and for small omega, you can write this analytic expression for the normal modes, and from this expression, you can see that why this is linear along any direction, and why it depends logarithmically along any direction. And for very small epsilon, I mean when your equal is very close to the horizon, you can this number is very big as compared to that number, and then you can approximate it by this equation, and so you can see that there is a huge degeneracy along any direction. And now if you compute now you know the omega, so you know the spectrum, so you can compute the partial function, and if you compute then from the partial function entropy, you will get exactly this is the lateral area of entropy. But for this you have to fix the one, like if you do in microcanonical ensemble, you have to fix your energy E to be the mass of the black hole, and of course the other thing that your epsilon must be down. And the position of the brick wall is also important to get this ramp, because if your brick wall is far from the horizon, you can see that your spectral form factor will not have any ramp. And so when your brick wall is far from the horizon, your spectral form factor looks very similar to the NPADS spectral form factor. This is the spectral form factor of NPADS. So you must place your brick wall very close to the horizon to get this ramp structure. Now you can ask, is this generic? So This is the fact that in BTC this is happening. For this, what we did, because we know that the near horizon geometry of all the non-extremal black holes are Rindler, so we compute the same thing in 2D Rindler, and if you compute the 2D Rindler normal modes, then this is the spectral form factor. But if you do the calculation in 2D Rindler plus S1, so you can now you compute the modes along this S1 quantum number direction, and along this S1 quantum number direction, you will see logarithmic dependence of the mode, and as a result, a spectral form factor will be translated. So this S1 is necessary. So one compact direction is necessary to get this deep temperature structure, and this along this compact direction, this is happening. Now you can do the same analysis for rotating BTZ also. There you have rotational parameters, so you can use the rotational parameter towards the extremality, and you can see what will happen at the extremality, because all the known microstate geometries are, most of them are constructed for the extremal black hole, and this is qualitatively similar, you can say, to this microstate geometry picture. So we can compare this result, and we have computed the normal modes for this rotating BTC background, and as long as you are away from the extremality, you will see this logarithmic growth and the deep plateau with the ramp up slope 1 in the grand canonical spectral form factor. So your partition function is not now z to the power minus beta e, instead it is z is equal to e to the power minus beta e minus beta. N is the m, angular momentum, and E is the rotation. So
what do you mean by microstate here? What do you mean by microstate?
Oh, so in general, this microstate geometry looks something like you have far outside it looks like black hole, but in the horizon region it's smoothly captured. So here also you have a big hole near the horizon. So far from the outside you will see a black hole like geometry, but at the near the horizon you have a pattern. So you hit something. You are not you will not have ingoing boundary condition there. And
usually, though, the microstate picture, the horizons where these different microstates are different from each other, right? You're thinking about the cap is where
yes, the position of the big is
that's beyond the effective horizon typically, though, right? So in the microstate picture, you have these different solutions, and they start differing from each other geometrically at some scale. You can identify that scale with a horizon. So that's, call that an effective horizon if you like. You're thinking about the cap as being the brick wall, though, so it's beyond the effective horizon. Is this right, or am I misunderstanding?
No, in our geometry, the brick wall is outside the horizon. So, but
in the microstate geometry, where is the brick wall for you?
I thought that it's like you have a black hole type geometry for outside, and it's smoothly captured. So you have some regularity condition.
Right.
At R equal to 0.
In the microstate geometry, why is there a big one?
That's what I'm
No,
asking.
I'm saying it's like
They say that there is a big one.
no, I'm not saying that. I'm saying that these are constructed for the extremal in most of them, and this is like you have from far outside it's like black hole, and the geometry is smoothly captured. So you will not have any ingoing operation.
Okay, but that's a completely different problem
Yes,
from this
yes,
one.
yes.
Okay.
So here what I am doing, I have a black hole geometry, and I am putting some big wall very close to the horizon. So I am saying that maybe then you can compare what happens to the normal mode here, and if you quantize the probe scalar in that geometry also, then what will happen? And the similar thing is happening, because here also we have computed the probe scalar, the quantization, so it's quantized omega along various quantum number relation, and it's also linear. And here also, in the extremal BTG, if you compute the probe scalar, the spectrum is also linear along n and n. That's what. So this is the corresponding spectral form factor with the linear ramp when the black hole is not at the extremal. Now, generally, this chaos implies thermality, but in black hole, this thermality arises because of the radius of the horizon, So it is possible here to see some thermal feature because we do not have horizon here. To explore this, let's focus on the Green's function. So using Sonsteiner prescription, we can compute the Green's function by taking the ratio of normalizable mode and non-normalizable mode and imposing the equal boundary condition inside the geometry. So if you compute the Green's function and if you plot, there are many poles of the Green's function. And if you decrease your Z now, which is the position of the big one, you'll see that these poles come closer and closer. And in terms of the bulk picture, this poles basically corresponds to the normal mode that we were computing. So what is happening is along both direction, along N direction and along M direction, these poles start coming closer and closer, and the rate at which these poles are coming closer is very different along the different quantum number direction. So along M direction, this is like A plus E log 1 over Z naught, and along M direction which is exponentially higher. So along M direction, the pole accumulation rate is exponentially higher as compared to N direction. So in the limit, when the poles are so dense that you cannot differentiate the poles and branch cut, you can do the branch cut approximation and you can compute the branch cut discontinuity. And if you compute the branch cut discontinuity, you will get this imaginary part of the black hole function. So we can read of black hole's quasi-normal modes and some other properties of black hole function by computing this discontinuity.
And you get the right answer. This is what we were discussing in the beginning. You get the right answer.
Yes, yes. I mean, so then you can prove this imaginary part of equal Green's function equal to the minus of imaginary part of the black hole Green's function. Now, if you compute the position space Green's function, then you will get the same thermal Green's function as you will get for the black hole with the same frequency. So, as long as your B core is very close to the horizon, so that you cannot differentiate the poles and branch cut, you can compute the position space Green's function, and your position space Green's function exactly looks like the thermal function with the same frequency.
This is what I was saying earlier, because the e to the I omega and the e to the minus I, those are conjugate solutions. So that's why we were comparing them to the imaginary. You're saying you actually get the right answer using the paper.
Now, in 3 dimension, we know that degrees of freedom of the gravity is 0, so there is no identical dynamical gravity. So, is it possible to find this feature for dimension greater than equal to 4? Linear calculations suggest that, and this is a generic fact, but it's good to show this explicitly. So, here we will provide explicit example for 5-dimensional areas towards the black hole. So, this is the metric. So, and you have some probe scalar, and due to symmetry of the metric, you can decompose your scalar field like this, and you can write the radial equation like this. And you can see that in the radial equation, you do not have m. So it is a huge degeneracy along this m quantum number. And this is a huge equation, and this can be written in normal form by changing this coordinate transformation. You can write it like this, and this is the near horizon behavior of the solution. So first one is outgoing, second one is ingoing, and this is the near boundary behavior of the solution. This first one is normalizable, second one is non-normalizable. So if the equal boundary condition is that at the boundary it's normalizable, and at the horizon, near the horizon, at some location of the equal z equal to z naught, it's 0. Now to find this normal mode, we need the connection formula. For BTC, this was like hypergeometric equation, so we know the connection formula. But here this is a Yoon equation, but there are some technique using Yoon COP, and those connection formula can be written approximately, and we can solve for the normal modes. And if you solve the normal modes, then these two normal modes are labeled by 2 quantum number L and M. This is the spectrum along L direction, and this is the spectrum along N direction. So along N direction it's linear, but along L direction it's logarithmic dependence goes at. And as a result, you do not have a clean ramp in the spectral form factor. Now you can ask like why this is happening. Is this the fact that we are in the higher dimension? But no, this is not the fact. This is happening because your R is over L is large. If you do the same calculation for BTC black hole also, if you compute the normal mode with this R is over L, you will also see that this logarithmic dependence goes up. Because the approximation needed to get this approximation, this result, actually not valid when your R is over L is not order 1. But you can show that when your R is over L is not order 1, let's say R is over L is 100, then for high line mode, high line omega, this approximation is valid. So for high line mode, you will have this logarithmic dependence. But because we are plotting this normal mode for large R is over L, because for small R is over L, when R is over L is order 1, we cannot, our numerics is not stable enough to compute the normal modes by using this Newman CFT technique. But we can do WKB analysis, and in WKB analysis we can compute the modes for R is over L order 1, and this is when R is equal to 1, and we get this is the spectrum along L direction, and this is the spectrum along N direction, and along L direction it shows again the logarithmic dependence, and as a result in the spectral form factor you have a linear ramp. And this similar pole condensation physics also happens there, so you can show that imaginary part of this function. In the last section, what we will quantize probe scalar in the collapsing scenario, because it's not a Dirichlet boundary condition. So what we have a 2 plus 1 dimensional collapse. So our shell is collapsing, and outside the shell the geometry is BTC, and inside the cell the geometry is globality. And we are trying to quantize probe scalar field in this geometry. Though it's not Dirichlet boundary condition, we will see that the pole accumulation phenomena occurs in this model also. So this is our metric. So and RS is the position of the shell. So inside the shell the geometry is globality, and outside the shell the geometry is BTC. So now we have to impose these two boundary condition. If you impose this boundary condition, and if you compute the Green's function using Son's tightness restriction, you will find this Green's function, where F1 is the solution of the Green-Gordon equation and is regular at the origin. Phi 2 plus is the normalizable part, and phi 2 minus is the non-normalizable part. Now you can find the mode by making this denominator equal to 0, and if you plot the Green's function here also, as the shell moves closer towards the horizon, you will see the effect of force accumulation. So it is for Rs equal to 10, and it's Rs equal to 1.0. So Rs means Rs over Ra. And also you can have some analytic handle in these two regime. First one is when the shell is near the boundary, then you can compute the mode, and these modes are given by this. So these are the NPADS normal modes. And when your position of the shell is very close to the horizon, you then also have some analytical handle, because the solution phi 1, phi 2 is simplified. But you will get two inequivalent boundary conditions. But there are some intuitive way to see this, why we are getting these two inequivalent boundary conditions, because in the limit Rs tends to Ra, F2 is 0, because F2 is R square minus Ra square, so it's 0. So first term vanishes, so you will have the second term. Now in the second term, the condition is this. So you can have phi 2 plus equal to 0, or maybe Taylor phi 1 equal to 0. The first condition, the phi 2 plus equal to 0, this is the Dirichlet boundary condition that we were previously used for BTC black hole also. And if you take this quantization condition, you will get the same normal modes and interpolate structure. But you can impose this boundary condition also, Taylor phi 1 equal to 0. If you quantize with this boundary condition, you will see that you will get modes which are linear along the quantum number, like m quantum number and n quantum number. So in the collapsing scenario also, this Dirichlet boundary condition scenario occurs when your shell is very close to the horizon, and you will get this differential structure. So I have taken my topic some direction. So we have observed that for large REs over L, the spectrum loses its logarithmic dependence. So the part of the spectrum that is responsible for getting the slope 1 ramp in the spectral compactor may depend on the value of REs over L. So maybe some getting a better understanding of this fact would be valuable, and we are currently trying this. And for VTC black hole, it can be shown that the scrambling time, which is the time an observer takes to reach from boundary to the position of the big one, this time you can extract from the omega versus n plot, because see this expression is exactly the time log 2 epsilon over RA. So you can extract this time from omega versus n plot. So is it possible to extract this time for higher dimensional black holes also? This is another fact, and we are trying to see if this is true or not. And maybe one of the most important question is why this quasi-degeneracy along the angular quantum number direction is happening. And she has suggested that maybe the probability computed from this Laplacian wave function can provide some insight into this, and we are currently investigating this thing. So these are some considerations currently working on.
Just to did not catch this properly, but which quantum number becomes log n?
Oh, so let's say for BTC, you have one quantum number due to the periodicity of the coordinate. Let's say this call it as A. And another you will get because from this radial equation, it's called n. Then you will call this a principal quantum number. So along n direction, if you fix n, store the logarithm.
I see in all the cases here. It's the angular momentum quantum.
What property of the spectral density does the ramp do?
Spectral density.
Yeah.
I mean, if you assume that your rho mu rho lambda is sine kernels, then you will get I don't know if you want to lambda minus m square. This is also right.
This level repulsion, right? And
Yes.
fixed.
In fact,
fixed
there is
in-
another question. So I'm actually confused on Suman's comment. Would you agree with what he said that the entropy is coming from large degeneracy in the leather space in the 1 over S?
Yes, entropy is coming due to the large degeneracy.
Yeah. But I thought the entire point of the spectral form factor was that it was about, at least the plateau, it's about the chaotic nature of the level space. Right?
It's not fixed. Chaotic nature is due to ramp. Ramp is due to chaotic nature, not Plato. You will get Plato in every quantum mechanical system. If you have discrete spectra, you will always get a Plato.
And question, what is the value of the plateau?
Yes,
The value of the plateau is equal to e to the minus
Minus
s by 2.
yes.
Maybe you see that here.
That
We
is
have not
by changing J cutoff and N cutoff.
Yeah.
That actually sets the dimension of the
Yes, so have you checked that you get the value of the plateau is e to the minus s by 2?
no, that.
So you are saying ramp is due to chaotic nature, but you are also saying there are large degeneracies in the spectrum. How is this working together?
Then you have to focus on this. If you have many degeneracies, then you have to focus on the symmetry result, and you have to discard those degeneracies. Like for this 5-dimensional case also, you have huge degeneracy because all this m quantum number gives you the same amount. And while computing the spectral compactor, I discovered that.
But isn't it a fundamental factor of black holes that the Lorentz spacing should be e to minus s? Where does that turn up in the different network?
Here S is fixed but controlled by the cutoff in J direction and N direction.
Yeah.
So yeah,
I don't think it should. I don't think it should be. How can you see e to the minus s in a code calculation?
You know?
You know,
And so that is a bit confusing, but usually people say that from the bulk point of view, this random level structure should correspond to non-perturbative or even doubly non-perturbative physics, whereas this seems to be a semi-classical calculation. In the book.
Yes, I mean, in the growth sector, we are seeing these.
So, you see that time scale of E is equal to 1000?
So,
E is equal to 1000 with basis in time of A and what is it? And E.
yeah.
So, why is such a large time scale? E is equal to 1000. What does this time scale depends on? The cutoff.
Time scale is, I mean, the deep time, the ramp time is depends on the cutoff, and also this J cutoff and is cutoff.
So, if the cutoff is 0, then what will happen?
Then you will get Gaussian or no, and then
okay, then we don't see any damage.